All right. So now everything is connected, and I know that everything is connected because I got here all green checks, right? This is essentially the main interface, and it doesn't have a direct use for my measurement. It just ensures that everything is working as I expect. One thing is the checks, another is the licenses, but this is a bit more of a less interesting part. The other is all the temperatures that I mentioned, right? So this is, for instance, the temperature of my heatsink, of my temperature controller. And if I click on it, I can manually start the heating, and you can see the temperature is now rising very quickly. And this one is the environmental temperature, is at the same level of the samples. And as I mentioned, temperature and humidity from this, the dew point is calculated. And this is an additional temperature sensor that we provide, is actually recording the temperature of the room. This is it essentially from this interface. I will not spend more time on it because the next one is a bit more interesting. Instead, this is a graphical representation of the sample holder. And indeed, you can retrieve, these are the 20 samples that I mentioned before, rectangular, shaped as a rectangle. And from this interface, you can start setting up the safety limits essentially of your measurement. And here, this is called as device properties. I call it limits because it effectively says it sets a limit that cannot be surpassed. So this can be the forward or the reverse current. Now it's the highest limits possible, but let's say I don't want my device to go into reverse current in any situation, then I just set it to 0. And whenever during the measurement I have a negative current, then it stops. The measurement immediately stops, and the device is disconnected, is electrically disconnected, so it doesn't, it's not damaged. Surface area, this is the active area of our sample, and with the voltage, maximum minimum applies the same as with the current. From this interface, you can also choose the polarity, the name of your samples, and also the polarity. This can be useful because essentially we design with a certain electrode polarity in mind, depending on the layout that you provide. But it might be that in the future you change the structure, you have an inverted structure with your device, and this means you can use the same sample layout, same sample architecture with the same sample holder, but the electrodes are inverted. What was plus before is then minus, and vice versa. This is why we have this feature, this software feature, that indeed allows to switch the polarity instead of making a hardware change, right? From this specific interface, you can also perform the resistance calibration. Now, I will just spend a couple of words. Now, because the system as it is now, it's a 2-wire sensing system, then the series resistance of any component can affect your measurement, right? And what I'm showing here is essentially an equivalent circuit that is representative of the whole system from Litos Lite to the samples and back, because it's our voltage source. This is the measurement resistor that is close to the DUT, and then you have these additional resistances, right? You got essentially the cable and the contacts and the connectors that are adding the series resistance, plus the ground resistance. With this calibration, you can compensate for that and have a precision, reach a precision that is extremely close to a forward sensing measurement. So in this way, you have on all devices, on all 56, maximum 56 devices, you have a calibrated system that is performing almost like a forward sensing system. All right, then I will proceed with an interface that is actually the most interesting part of the software from my perspective. From this, let me actually make screen a bit bigger. From here, you can essentially create your measurement. So as you see, we have 3 columns. We have a recipe list, and the recipe is essentially a combination of steps where a step is a function of the instrument. And this means it can be a measurement like a JV or stressing, or it can be the temperature control, for instance. And you can combine all of these and come up with a measurement that you prefer. Let's just start very simple. We have a new recipe. From here, we start from nothing. Let's say I just want to perform a dark JV and then a JV under illumination. Then I will just have my JV. I choose the devices that I want to measure. I select the voltage range, let's say from 0 to 1 volts, and how quickly the scan rate should be, how many millivolts per second should be used, and also the scan direction. And this is my dark JV. Then I add the light. In this case, I want to do one sun, so 100% with our sun simulator. And then actually, let's do something more clever. And then I just replicate the same step, put it below the light intensity. And then essentially, when I start this measurement, I will first have a JV, then the light turns on, and then the same JV as the very beginning will be performed again on the same samples. Let's add another step. This is a stressing step. And we call it stressing and not MPP tracking because it's more than just MPP tracking. You can choose whether you want to perform indeed MPP tracking, or you can set the device at a fixed current. In this case, 0 ampere would mean VOC, essentially conditions, or 0 volts. This is JSC conditions. And maybe you can have another sample that I want to stress at reverse bias condition, and I just put a fixed negative voltage. So you see, we call it stressing, not MPP tracking, because in addition to that, you have fixed voltage or current condition, and each one individually for each device. Or you can say, let's pick all the devices and we have all of them at MPP tracking conditions. Up to you, depending on your preference. From there, of course, you can define the duration of your measurement. It can be 1 hour. It can be also 10 days. Up to you. And also the point rate. So essentially, the frequency of your data points. In this case, it's very dense. It's 6 points every minute. If you have 10 days of measurement, maybe 6 points every hour is enough. So these are the 2 main measurements. We can make it a bit more interesting. Maybe we want everything at similar to STC conditions, so standard testing conditions. And then we have a temperature that starts at 25 degrees, and this will be maintained throughout the whole measurement. Unless I add another temperature, for instance, and here I say I want another temperature, but this time I make it at 75 degrees. So then I have the JV at 25 and the stressing at 75 degrees. You get a bit the idea. Actually, let's make a new recipe. One powerful function is this sweep function. Sweep step, actually. It has 2 main functions. And the most simple one is to set it like this. So you have essentially a counter. It goes from 1 to 3, or it could be from 1 to 15. And whatever is inside of it. So as you can see, I moved the JV step inside of the sweep. Now it's outside again. Now it's inside. Whatever is inside, it could be also a stressing step if you want, will be repeated up to 11 times. It's probably excessive, but it makes sense if you have devices that don't always act the same, right? Don't always behave the same after each measurement. Let's remove this one for now. Oops. So for instance, if you have 15 times the same JV, then you're building statistics over the over the measurements essentially, right? Then you can have a median of all the JV, and this means a median of the fill factor, VOC and JC, and see and have an idea of the behavior of your device. If you had, as I had before, a stressing step, let's select everything, and maybe the stressing step lasts 10 hours, then you have the JV plus the MPP repeat. So this is essentially a way to have to alternate JV with stressing, or the other way around, MPP tracking with JV. So in this way, if you proceed for 15 times, then you have 150 hours of stressing, and throughout this 150 hours, you also have the JV. So in this way, essentially, you can follow both the MPP and also the PV parameters over time, because as you take a JV every 10 hours, then you have the evolution of the VOC, fill factor, and JSC as well. Now, this is one possibility on how to use the sweep step. The second that I like is to use the variable inside the sweep. You see here, we have a variable. It's called X. It can be Y. It can be a name. It depends, up to you. And you can use it for any measurement parameter. Now, a simple example is I have it here, and I put the X between curly brackets. And now, okay, let's change maybe also the voltage. Sorry. Now the scan rate is a variable, which means it varies depending on the values that I set here. So I set a starting value of, let's say, 75 and a stop value of maybe 150, and the step, so essentially how it will advance, of 25. This means that with my JV, I will start with the first JV with a scan rate of 75 millivolts, then 100, 125, and then 150. So in other words, you're doing a scan rate study. And in this way, you can understand what is the ideal scan rate for your device, and you can have an idea also about hysteresis of your device, right? If you vary the speed of your JV, your device will respond differently. Now it can be a JV with a variable, but we can also do another thing. We can add yet another sweep, and inside of this sweep we add a temperature. Where is it? Here. And now I call it Y, and then my temperature becomes a variable. And maybe I want the temperature to go from 25 to 50, maybe, with a step of 5. And the sweep that I prepared before, I put it inside of the sweep for the temperature. So you see now it's a sweep in a sweep. In this way, I can do this scan rate study that is also temperature dependent, right? We have now the temperature that varies. Essentially, I set the temperature of 25, then perform the scan rate study, then increase the temperature, then the scan rate study again, so on and so forth. So you can see it's quite a powerful feature, and it allows you to be creative with your recipe. One very last important and very recent feature is this Python step. It essentially it's a function that it's a step, to be more correct, that allows you to control any electronics that can be controlled with a Python script. So you see here you have a script path. If you choose file, then you have you can explore through your folders, load the script, and then within the script you will have a function that must be named, and it will be recognized in this way by SPM, and the argument essentially is the value that you give to a function. So it can be the function can be turn on, turn off, and then the argument is on or off. or it can be the light intensity, it can be the movement of a shutter, it can be the temperature of a heating plate. Essentially, any electronics that can be controlled with a Python script, then it can be controlled also with our software SPM. Now, this is useful because then you understand that all the control, all the electronics are within the same software, so you can combine together with the measurements, essentially, with the control of the measurement, this new electronic and add flexibility. Essentially, you don't need to have a separate software for the separate electronic and then be there and start everything on time and make sure that everything coordinates. It's all within one software, and you can control it all. Now, the next will be for me to show you how a measurement performs and how the data would look like. In the meantime, I will prepare very quickly a simple measurement that I will perform on the samples that are loaded now, and so that we can show you how it works. So we just start with a simple JV. Goes from what is it, -0.1 to 1.5. Let's make it not too fast. All the samples, and then we perform the same JV with and without light. After the light, we have a temp. Well, let's start with the temperature actually. And one thing that is important, we always had a wait time. We don't need to wait. I would just put it there. So we always recommend once the temperature is reached, it's true that the temperature is there. It will be the effective temperature of your temperature controller module, but it's not necessarily the temperature of your sample. So we always recommend to wait 5, maybe 10 minutes so that the temperature distributes, homogenizes, and then you have a good starting point. And then as last step, I will have, where is it, the stressing. We can do a short MPP tracking. We can make it 5 minutes. We will need a lot of data points. Let's make it, 10 should be enough. And then let me start the chiller, just a second. So with this sun simulator, we need to start a chiller because otherwise it overheats. So now I'm happy with my recipe, and I will quickly start it. You see here the play button. As soon as I will click it, a new window will pop up, and this is the live window. Essentially, it shows how the measurement is going. It starts with the temperature. You see now it's cooling down. It already reached 25 degrees. And now we are at the wait step. We can skip it. We can move on to the JV. Let's see how the samples perform. Now this is dark JV at 25 degrees. Okay, we got one sample is performing okay. Yeah, actually two are okay. The other one has a bit of hysteresis. The light is on. Now you see the current is negative because it's generating current. Now it's only forward direction, right? So I start from negative and I go to positive voltage. We cross the VOC, goes out to 1.5 volts, and now we are at the stressing step. You see here, points appear. It's searching for the MPP tracking, for the MPP point, sorry. So you see, initially it has a jump because it starts from a voltage close to the VOC, and then it makes large voltage jumps until it reaches the MPP. Once the MPP is reached, it will keep tracking the MPP. The algorithm that we use is called damped, perturb, and observe. Essentially, it's a modified version of the perturb and observe algorithm. It's very common. Apply small voltage, and if the small voltage variation, and if the power increases, then this will be your next voltage. If it doesn't increase, then you stay at the same voltage where you were. So now you see stabilizes. Okay, now we should have enough data points. These are very poorly performing devices, so this is why probably it's taking a bit longer to stabilize. Otherwise, it will take a couple seconds. But now essentially we are good to go, and I will stop it here. One feature that I would like to mention while the measurement is running is that you can disable devices while you're performing, for instance, MPP tracking. If you see that one is shunted, for instance, you can just disable it so that it's not recorded anymore. Then I will stop it. And here we are at the results interface. And you see this is the list of samples and pixels. So in this case, I have 1 pixel for each sample. We have customers with which have up to 8 pixels on a single sample. And you can visualize each measurement that was performed. Now here you have a timeline. So it literally follows, as you can see, the point in time when the measurement started. So you have a date, you have a time, and you can multi-select the measurement, or you can choose 1 pixel and see all the measurements of that specific pixel. You can edit a bit the view so that I can see more clearly my data points, you see. And then you can also zoom in to see how it behaved, maybe close to the VOC. You get an idea. This is definitely not a plot that is ready for your next nature paper. We are very aware of it. It's not the most beautiful plot, but it's what is functional enough and useful to understand how your device is behaving. You have also a quick summary of the PV parameters here on the side. So fill factor, VOC, ISC, also the efficiency, of course, of all your samples, and also the testing conditions, as you can see. And then if you go to the stressing step, now you see this is the voltage. Let's see first the power. So this is what we were seeing during the live view. You have multiple plots here on the side. So let's starting from the voltage. As I mentioned, you start close to the VOC, and then you drop down until you reach a voltage that is close to the MPP voltage. In the Litos Lite, we have voltage sources. So the current is what is measured and calculated afterwards. And of course, depending on the voltage behavior, then you have also your current behavior. And then you have your PC, of course, comes from the power, and also a few data points about the environmental, about the sensors that I mentioned. So you have the temperature, you have the humidity, how it was changing, as well as the temperature of your temperature controller. Now, it looks like it's very unstable, but if you see here on the scale, it's actually right on 25 degrees. It's just a minor changes. You can just make the scale a bit more meaningful. So just between 24 and 26, and you see it's right on point and 25 degrees. And from this, the next step would be, of course, to export, maybe elaborate a bit more the data, or make it ready for your paper. You can export it as a CSV, so Excel file. And from this window, you can choose the type of measurement and for which pixels, but you can't choose the specific measurement. So if I proceed in this way, I will have both JVs for all the pixels. But if I want only one JV, for instance, for this pixel, then I will just right click, export, and this is a specific export for this measurement. And an alternative export is also the JSON. JSON file is essentially a text file because you're not used to it. And it's very convenient because it's very compact. It's all in one file. If you're into programming, you can create your Python script to plot it. If you have access to any AI tool, you just give it to the tool and it will plot everything in a matter of a couple minutes. So it's rather convenient format. I personally prefer it over the CSV, but yeah, depends on how you work. All right, this is an overview of the software and how the instrument works.